The topic of the video is the quantum mechanical problem of hydrogen atom. The hydrogen atom has got a proton and an electron, and let us take their positions as the triad Xe, Y, and Ze for electron, and then the triad X sub p, Y sub p, and Z sub p for proton. And let's call them as vector r sub e and then vector r sub p as shown in figure number 1. And let's assume the wave function for the system of hydrogen atom as psi, which is dependent upon r sub e and then r sub p and time t. Then the probability of finding electron between these r and re plus delta dre, and the proton between the locations r sub p and rp plus drp is given by this product here. Then the Schrodinger equation for the system can be written as IH cut into dou by dou t of psi is equals to H psi, where this H is actually the total energy of the system, which is the Hamiltonian operator of the system, and so that we can write as the summation of kinetic energy of electron and the kinetic energy of proton. And we can also write down the term of the potential energy of the system as this. Since the momentum of electron and momentum of proton can be expressed like these products, we can actually rewrite the Hamiltonian in terms of these momenta. And then we can also take the fact that momentum operator P is IH cut into del operator, so these P squares will become kind of del squares for both electron and also for proton. And so the Schrodinger equation will actually turn into this form here. And then if you take the solution for this equation, solution as a psi, which depends upon Re and Rp, and T is equals to exponential minus this kind of epsilon T divided by H cut into chi Re and Rp. That means we are taking the solution as a stationary states. So if you do that, then we'll actually get this thing in the bracket, which with del square operators for electron and del square operator for proton, and then V in place of the potential energy acting on chi is equals to epsilon into chi. And to solve this differential kind of equation, we actually take a transformation from Re, R sub E and R sub P vectors to the center of mass coordinates vector R, and then the relative coordinate small r, where they are defined like this. And we can also have the definitions for del squares in terms of those new vectors like this. And if we make this transformation, we'll see that this 1 by me into del square in terms of electrons, and then 1 by mp into del square in terms of protons coordinates equal to this quantity here, where mu is reduced mass defined like this, and then capital M is total mass of those particles. And this chi also will have the dependence upon r and then the small r like this. So the Schrodinger equation will, Schrodinger equation that we had as the partial derivatives in terms of del squares will be actually kind of looking like this now. And to solve this, we can make use of the fact that we can separate the variables dependent upon capital R vector and the small r vector as a product like this. So if you substitute this equation into the above equation, we'll get this one. And then if you divide this equation by again phi of r into psi of r on both sides, we'll get this equation. And if you take the right hand side, which we had epsilon as e sub r plus e, such that this first term is equals to this e sub r, then these two terms, the remaining two terms should be equal to this e. And if you rearrange this, we'll do it a bit later, but if you rearrange this equation, it will turn into this form. And if you actually take phi of r as a plane wave like this, then the above equation for the capital R coordinates will give you this E sub r is equals to this quantity. And for relative coordinate, we have this differential equation for psi of r. And if we express this del square in spherical polar coordinates, we get this expression here. And to solve this, we take a solution psi of r as some function y, which depends upon the theta and phi, and then some function capital R, which depends only upon the small r. And if we substitute this into the above expression, we get this expression here. And then if you again divide this equation by y into r, that means the right hand side of this equation, then we get the separation of variables like this. So we can actually see that the r dependent terms are actually in a bracket like this, and then the theta and phi dependent terms are in another bracket like this. So we have separated the variables r and theta phi into two different terms. And if you call this square bracket stuff as with a minus 1 by y in front as l into l plus 1, then we'll find that these y will become ylm theta phi's, which are spherical harmonics. And then for radial part, we get this equation, and this is what sometimes is called the radial part wave equation of hydrogen atom. And of course this function r is just a function of small r, so we can even replace dou r by dou small r is equals to d capital R by d small r. And if you do that, this equation will be actually looking as equation number 1 in Roman notation. And to simplify this equation, we actually define another function u of r, which is equals to small r into capital R. Then if you do that, we'll see that this d by dr of r square into dr by d small r will become like r into u double prime. And after substituting this into equation number 1, then we get this equation as our radial part equation. And by multiplying on both sides of that equation by u, we get that turning into this form, which we can actually say equation number 2. For small values of r, if you want to find out how the u function will look, we can actually multiply the equation number 2 by r square on both sides, and we get this. And in the limit of r going to very small numbers, we'll see that this will actually go to 0, and then this also will go to 0. So we get this looking equation turning into this form now for small r's. And to solve this, we can actually take the solution as u is equals to r power a. And if you do that, after substituting and simplification, we find whether a is equals to minus l or l plus 1. That means the general solution for u could be a linear combination of r power l plus 1 and r power minus l. And if you do not want to have the explosion of u at small r's, we can put this factor b is equals to 0. That means u should be something like r power l plus 1 for small r's. And for large values of r's, we get the equation number 2 turning into this form. And if you simplify this, it will look like this. And for bound state of electron and then the proton system, we can have the energy negative. So if you take the second term with a negative factor, and if you define something called lambda square as this factor here, and that equation will turn into this form. And to solve this differential equation, we can take solution as e power a into r. And after substituting this and simplifying, we find a can be either plus lambda or minus lambda. That means your u can be either e power lambda r or e power minus lambda r. And if you want to not to have explosion of u when r goes to infinity, we cannot take e power lambda r, but we should take e power minus lambda r. And now we can say that from the asymptotic behaviors of u, we can say that u can be a product of r power l plus 1 and e power minus lambda r and some function which depend upon which can be f of r, as equation number 3 here. And we can actually find out du by dr's when you add u as this form, as it's actually derivative for this first term, and then these two terms are put together like constants, and then the first term is kept as constant, and then the derivative for these two terms. And if you do the expansion, if you do the derivatives of these things, we'll see that it will look like this now. And then if you actually kind of simplify, it will take this form. And if you want to do the derivative of this du by dt to get d square u by dr square, then we start getting all these big thing, which after simplification will look like this here. So now our equation number 2, which involved u prime and u double primes, will look in this form. And if you multiply this equation by 2 mu by h cut square on both sides, it will turn into this form. And then if you actually make use of the fact that lambda square is equals to minus 2 mu e by h cut square, we will have some cancellation of terms. So we get the differential equation for f like this, which we can call as equation number 4 like this. And to solve this differential equation for f, we can assume it like a power series solution or summation like this. And we'll see that if you take df by dr, we'll get this expression, and then the double derivative will give you the second expression. And if we substitute this into equation number 4, we actually get this equation here. And if you write r power minus 2 r power k minus 2 terms first, and then r power k minus 1 terms later, we get this and in the next step we can take even this term which is 2 into l plus 1 by r with a factor k, and then bk into r power minus r power k minus 1 into incorporating in this term. So we get this one. And then if you write the remaining terms with r power k minus 1, we get this. And in the second term, if you take k minus 1 in place of k, which is this term, then we get the summation going from k is equals to 1 to infinity, and then instead of bk we'll be writing bk minus 1 and then r power k minus 2. So the recursion relationship that we get for bk is this equation here. and that if you rearrange will give you the ratio bk by bk minus 1 as equation number 5. And in the limit of k going to infinity, this bk divided by bk minus 1 will actually look like 2 lambda by k. And for exponential 2 lambda r, which can be expressed as this summation, if you take the ratio of the kth term and k plus 1th term, we see that it will be 2 lambda by k, similar to what we had earlier. So we can actually say that f of r could be e power 2 lambda r. Therefore, the solution which we had taken for u as r power l plus 1 into e power minus lambda r into now e power 2 lambda r will turn into this form. But to have physically acceptable results, this function f of r cannot be an infinite series. It should be ending with at some order, at some n. So that means all these coefficients b sub n plus 1, n plus 2, etc., all of them should be 0. Equation number 5, which was giving us bn plus 1 divided by bn, this thing, if you put b sub n plus 1 is equals to 0, will give you this equation. And if you actually take L plus capital N plus 1 is equals to small n, which later on we'll call as the principal quantum number, then we see that lambda into n is equals to this quantity, but we know that lambda was defined like this. It's a square root like this. And then so if you actually kind of solve for energy E, which we can even take E sub script n, then we get this equation number 6 for the energy. And in fact, this is the energy for hydrogen atom, and it says that energy is quantized. And we have seen that f can be an exponential function like e power 2 lambda r, but it cannot be the solution because it cannot be infinite series. So to find it out exactly, we'll again go back to that equation number 4, which is this one, and then we take the solution, we take a transformation of r into some kind of thing called rho, which is defined like this. So we can actually say that a small r is equals to rho by 2 lambda, and then dr is equals to 1 by 2 lambda into d rho, and then r square is equals to 1 by 2 lambda square into rho square, or d r square is equals to this thing will be constant, and then d rho square. So your f double prime will turn into this form, and f prime will turn into this form. And if you say that under this transformation the functional form also may be slightly different from being f to small g, then if you substitute all these things into equation number 4, we get this expression. And by writing 2 lambda power plus 2, and then here also plus 1, we get this expression. And if you write 2 lambda square as a common factor outside, and if you make use of the fact that your n was this thing actually, that is from the definition of lambda, you can write this entire thing as your small n. So you will get that differential equation of this form now. And if you compare this differential equation with the differential equation for associated Laguerre polynomials, which is like this, we can actually take the g function as associated Laguerre polynomial, which is defined like this. And then we can even say that f of r, instead of expressing, if you express rho as 2 lambda r, we get this form. And if you take the lambda as 1 by a naught into small n, where a naught is Bohr radius, this f of r will look in terms of the that a naught like that. And we can write down u, which was a product of r power l plus 1 into exponential minus lambda r into f of r, taking I mean in terms of this small r, when you express f of r as this associated Lagrange polynomials as equation number 4, I'm sorry, equation number 7, in which we have got these n sub small l nl as the normalization factor. This factor can be actually found by normalization condition, which is equation number 8 here as a differential equation. I'm sorry, as an integral. But the Lagrange functions have got the normalization condition as equation number 9. So if you write equation number 8 for r is equals to rho by 2 lambda, we get this integral. And this can be written as these constants outside and then integral like this equal to 1. But from equation number 9, this integral should be equal to the RHS of that equation number 9. So for n sub small nl squared, we can actually get this expression here, and if you make use of the fact that lambda is equals to 1 by a naught into n, we can write it in terms of a naughts like this. So the radial wave function for hydrogen atom will look finally as this, and then we can call this equation number 10. And this is the radial wave function for hydrogen atom. That's it in this video, and thanks for watching.